you stop for a month, and there's going to be a bit you've missed.
Well, we've already done that. I think there's a new release comes out today. So the way it goes. I think we'll get started then. I'll introduce myself. My name's Stu Christie. I'm based in Arizona. And my day job and my morning job is teaching classes, currently in OpenVino. Our team also does retail classes, so digital signage and pieces like that. And then we also do some industrial classes. So as I say, we're currently doing OpenVino. My colleague Shane, you want to introduce yourself, Shane?
Sure. My name is Shane. Same type of jobs, right? We're doing the OpenVino training classes and also helping the creating contents for other types of training. We're joining all the different events to build the ecosystem of Intel developers. That's about that.
Yeah, sounds good. So a quick look at, let's see if the slide's going to advance. Let's do clickety. Oh, let's go click. Nice. Oh, that's fun. I've got slide 1. Accelerator, and then we've got one little class on different types of what we call the heterogeneous plugin, different models in one application, so a bit more advanced pieces, so you can use the FPGA and the Movidius, or the CPU and GPU together. There's some APIs available for that, so we'll cover that. And then we'll have you register for access to the DevCloud, which is our online computing platform for AI, and we'll step you through some of the labs on the DevCloud and then set you free to run through the rest of those labs. You will have to register for the Dev that we'll put up on the screen when we get to that stage. So without much ado, we'll skip gaily past the optimization notice and the Intel legal notice 1 and legal notice 1 of 2. There will be a test on those later. Okay, so we'll start off with video, the eye of IoT. So we've got a few marketing slides up front. I will apologize for that, but hey, that's the way it goes. So these days, video, they're saying it's the eye of IoT. It's really being used at a lot of places, all of these places that you see on the screen, as a sensor. But as a sensor in all of these things, so emergency response and financial, the banking will be taking photographs of who's coming to the terminal. Machine vision, so computer robots that can see, basically. Smart cities and transportation, so those are cameras looking at us. And then autonomous vehicles are cameras in cars also looking at us, but unless you're in the back seat. So we've got some models that we'll be showing later that are derived from some of the autonomous vehicle pieces. Responsive retail, so we're say we so digital signage, and we've got some examples of that, so you can see how age, gender, emotion detection is done, head pose. Are people actually looking at these retail signs? Manufacturing, so smart manufacturing, that's often used for machine inspection. We've got some examples of that, although there's a lot more detail in our retail class on that one. And then public sector is government. We've got the cameras and drones are being used for fire inspections and things like that. So that's some of the pieces in there. So we'll cover some of those as we go along, but if people got questions about that, we can cover them as well. So the next slide has a quick overview of why this is so popular and probably why you're at the class, is that the deep learning usage is increasing. So if you're not using it soon, you will be, or your boss will be asking you to if you can use it. And one of the reasons is you can see the slide on the left. It's now got to the stage where the computer vision with deep learning is more accurate than humans. I would like to point out that there is a human error rate there. So not only do humans make errors, but the computers make errors as well. So now that's why there are ethical questions about face recognition algorithms and things like that, because there's an error in there, just as there is an error when people are trying to identify people. But these days, the computers are more accurate than humans. Hold on, I've got an Alexa here that's got a computer trigger on her, so she's going to keep talking. So the slides, the two pictures on the top, on the left, the top right one, sorry, on the right, shows the figure skater and traditional computer vision, so OpenCV with HAR cascades and those sort of things, generally can't identify that figure skater. And for some reason it's because she's only got one leg visible, she's tilted at an angle, she's a person, generally speaking, but the deep learning computer vision pieces can detect those sort of things. And that's another reason that computer vision and deep learning is being more and more popular. It's more robust in different situations, so different lighting, different angles where people are there, cameras at different heights than the cameras being trained at, or the models have been trained at. Those things are what makes this deep learning more popular and more accurate than. Today, what we're going to cover is just one of these segments in this circle. Generally speaking, if you're starting from scratch, you start at the import section with an awful lot of data, images that need to be tagged. It's a large, onerous task. Used to be done by humans. Now you can get the computer to do the training. Certainly if you use some of the cloud systems, so you can get back tag models. The other thing is it's been around for long enough that tagged information. But if you want to create your own particular trained model, then you need to get your own data. So if it's, if you're working in a factory that's proprietary, obviously, then there's not going to be public data sets out there. The models have to be created. We recommend, at least at this stage, if you're starting off, is to pick up a public model and go with that, unless you literally are in the business of creating models. And then you take that data and build your model, or take the model and then you train it. And generally speaking, those training things take a very long time. Those are the compute intensive pieces. It generally gets trained either in the cloud on large cluster machines or on NVIDIA graphics engines. These are compute intensive things, take a long time, can take multiple days. We've seen systems take weeks to do the training, even on these high-end systems. So not something that's easily deployable on an edge device, but deploying the model is basically what we're going to cover today with OpenVINO, where it takes this trained model with your application code, the constants are all fixed and everything, and we deploy it to an edge device. And that's the sweet spot for OpenVINO, to be able to take all these models, put them out there, and run efficiently, low power, fast enough for your application, optimized for the requirements that you've got. So we'll skip back a bit and look at this deep learning training versus the inference, just a bit more. And lots of labeled data. Now, if you put in a picture of a strawberry and you push it forward, and the system identifies it on that forward path as a bicycle, you send it back in, say there's an error, retrain the model. Multiple epochs, or what they're called, as these systems go through the training phases. Once it gets accurate enough, and that's your determination, the model weights are locked. So they're now set. And then we can move over to inference. And in this instance, when we put in a color and push it through the model, it should be able to detect the bicycle for us. So that's the inference part is what we're looking at. Say training takes a long time. It takes a long time and a bigger time if you've got a bigger data set. It takes a longer time if you want more accuracy. So there's a trade-off there, how much money you're willing to spend, and how long you're willing to take to train your model. And that brings us to choosing the right hardware. So we've got that graph on the right, and you can see there on the y-axis. The computer itself, or the CPU, is the most flexible. You can program it. I'm gonna have to switch that Alexa off. The CPU is the most accurate. Most flexible. You can get it to pretty much anything you want. Next up in computation flexibility, or less flexible, is GPUs. They're a bit more less flexible in tools for them. FPGAs, it's a strange sort of thing there. They're totally flexible in the ways and the means of hardware, but you need a piece of program to run on it. So there's a trade-off there between the hardware and software flexibility. And then Vision DSPs and dedicated hardware are in effect fixed hardware. So they're not flexible for computation, but they tend to be dedicated pieces. They will do that particular thing very quickly and very efficiently. And really, it's a trade-off. If you're starting, obviously, way up the arrow until you find the cost and price performance that you want. And it really varies, not only within different applications, but within a specific industry. So, we've got some guidelines and we've got some use cases if you're starting off from that. But generally speaking, it's entirely flexible and entirely up to you what you want to do and which devices you want to run this inference on. To make that not even easier, but to make the whole range of software and hardware that Intel supplies for computer vision piece that we're talking about today. So all of the hardware. Hold on a minute, I'm going to shut off Alexa. She's gone, hopefully. Never been upstaged by a computer before. Well, not quite so badly. So computers now. So computer hardware at the bottom, all the different cores we run across. Obviously our processor cores at the bottom there, you can see the Area 10, the FPGA, and the Movidius devices. These are those neural compute sticks that we're talking about. As you move up the stack to the libraries, we've got everything from libraries to help you write, or the ones that we use to write OpenVINO, and acceleration libraries that run on these hardware. The next level up is the frameworks. So there are optimized frameworks for Intel hardware. So we have gone out and worked with all of these frameworks. So the libraries. So just the Intel version of Caffe runs faster than the download the plain one from Caffe from GitHub, for example. So those are all available as well if you want to run models or do some training, even with these frameworks. I highly recommend you get the Intel optimized distribution. And then the tools, that's where Intel distribution of OpenVINO fits into, but we also got Parallel Studio, System Studio, which are compilers and debuggers, the SDK for OpenC to program the GPU and the FPGA at the low level, so we've got that toolkit available if people want to optimize their or optimize the pieces that we've done for OpenVINO or extend it. And then up top we've got all the different diagrams or logos representing the pieces that we saw at the first slide, the eye of IoT, the different use cases in different industries where this is being used. So OpenVINO is the toolkit that we're going to be concentrating on now. It's a toolkit that's on the edge devices. Say it uses CPUs, GPUs, multiple accelerators if you want. It's very high performance. We'll show you some of the graphs as it goes through from the earlier versions through to the latest versions. Say they call it heterogeneous. We can run the same model across multiple pieces of hardware. So you write it once, write your application once, get it going, and then you can choose the hardware without changing the software to determine the performance and the price you want to pay. The URL softwareintel.com OpenVINO toolkit has got the software, and there's also an open source version at o1.org OpenVINO toolkit, or if you look under OpenCV on GitHub, it's also there, and it's part of OpenCV these days. Almost all of it's open source these days. I think there are certain pieces that are still not. For example, the FPGA plugin. So there's some proprietary pieces in the FPGA plugin that are still shipped in binary only. Inside the toolkit itself, it's effectively split into two pieces. Well, we've got three actually. Deep learning, traditional computer vision, and then tools and libraries. So we'll start with traditional computer vision up in the top right, and those are libraries for OpenCV, OpenVX, and we've got a bunch of samples. So those are things for the OpenVX is used for it's a set of kernels and primitives used to accelerate things like computer scaling, recoloring. What else was in there? They will run on a GPU, actually on any OpenVX supported hardware. OpenVX is a standard that the industry supports, and you can have a look at that. You'll see, it's in effect a hardware optimized subset of OpenCV. OpenCV is what we use in most of our samples for getting the original image from, say, the camera, processing it, scaling it down, pulling it apart frame by frame, and then also, because we're running samples, we use it to annotate the output so that people can see that OpenCV, that draw frame rates or draw bounding boxes and things on there. So OpenCV is used for those sort of pieces. Deep learning piece on the left is, let's say what we would call OpenVINO, or what the people that use it tend to think of it as. And it's two major components, at least at this stage, is the model optimizer on the left and the inference engine on the right. So the model optimizer takes a pre-trained model, runs it through this model optimizer, which is a set of Python scripts. And we end up with this, what they call IR, it's an intermediate representation. It really consists of two files, and the other one's the binary, the weights. It's a bin file. It's all the pre-trained weights that we talked about earlier. And then those are passed through to the inference engine as part of your application. Python, C++, we've got Go applications, for example, on our GitHub. And the inference engine that it gets passed to is dependent on which piece of hardware you've chosen. But it's independent of that. So you run the model optimizer, you pass it to an inference engine, the same application, same model, same IR file that we support. The Open Model Zoo has a large number of pre-trained models. I think there's over 100 now. Large number of samples. Some of them are for API tests, so they're fairly simple. They're not quite hello world, they're hello classification or hello something else. So if you look at the hello samples that are delivered, you see their single API calls, how to call an API to do simple things. There's a model downloader that will go out and download a large number of models from Cafe, MXNet. I've forgotten the other ones. 4 or 5 different. We'll see those later. And then the Deep Learning Workbench is a GUI that bundles up the calibration tool, the model analyzer, the benchmark app, some accuracy checkers, and a few other capabilities into an easy-to-use GUI that allows you to run multiple inferences and figure out batch sizes or number of streams or number of concurrent inference requests that should be sent out, and allows you to determine graphs and figure out, okay, this is this thing I should be choosing. I should be running this particular on this particular device. It allows you to choose the GPU and CPU, and I think the Movidius NCS chip, and figure out, run multiple pieces on through a GUI. Much easier to use than running a command line. Gives you a nice graph output of what's available. The tools and the libraries, there are extra pieces that are added in there. So the Intel Media SDK allows you to use the hardware encode and decode within the Intel chips. So H.264 encode, decode. So if it's sending MPEG or H.264 pieces, you need to decode that into a particular frame and send each frame at a time to the inference engine. And then if you're converting it back into video and saving it, then the Media SDK helps with that. And then the FPGA comes with a separate set of a separate distribution actually for Linux. It's available for Linux only at this stage, and it has a runtime environment that is loaded onto the FPGA, a bit like a bootloader in some effect, and a set of bit streams to the FPGA that have been optimized for different models. So there's a Google Net one or a SSD one. These bit streams have been set up and optimized, and there's I think about 20 or so of those, or at least a screen full of those that are readily available. Operating system support. Ubuntu is the most popular one. So most of our samples and everything are set up for a Ubuntu distribution. We support Ubuntu 16 and also CentOS, which is a Red Hat based operating system. Obviously with Microsoft Windows, and then Yocto Project, which is an embedded OS, embedded Linux. And then the Mac OS is supported for CPU and the neural compute stick at this stage. And the reason for just supporting those is that this is an edge inference toolset, and you can't really be deploying a Mac laptop on the edge, say on the lamppost outside, and watching traffic, trained and everything, and optimized on the Mac OS. But ultimately, it would need to be one of these embedded operating systems and I would say a sealed device, smart camera, whatever, running one of these operating systems that's deployed in the field. The pieces on the bottom show the different pieces of hardware that are currently supported. There's a little bit more detail on the toolkit. So you'll see we interchangeably use two names for OpenVINO. OpenVINO was it the Intel OpenVINO distribution version? So it's the branded one, and then the Intel Deep Learning Deployment Toolkit, DLDT. I can't remember how it works. That's the name that's given to the open source version. Right now they're equivalent, so it really doesn't make much difference. But if you want to run it on, say, a different operating system than the ones we support directly, then you can take the open source version and compile it for. We've got people using Mint Linux, for example. Excuse me while I have a drink. So the model optimizer on the left, say it takes in trained models. It pulls in Caffe, TensorFlow, MXNet, ONNX, and Caldi at the moment. And through ONNX, we support Caffe 2, PyTorch, and a couple of others. They can all export their models into the ONNX format, and we can read them that way. We've had people at hackathons, for example, take a model that was supplied by Apple for the Apple ML for the phones. They could export it to ONNX, and then we could read it, and then we could run it on an Intel hardware. So the model optimizer is a Python tool. Generally, it takes 10-15 seconds to run and convert/optimize a model. We've got more slides on it later that will show the sort of things it does when we talk about optimization. You can effectively just switch it off and do the conversion, so you get the same model brought right into OpenVINO, the original models. Comparison, you can do that. And then the Inference engine comes with, well, we've got here 6 different plugins. The CPU plugin and the GPU plugin and the Myriad plugin, and actually now the FPGA plugin, offer extendability pieces. CPU, we extend it with C++, and the GPU, FPGA, and the Myriad, they're extended using the OpenCL SDK. So the kernels that they run for each layer, OpenCL, and we supply example code. We've got a small training session on adding extensibility for a new layer, a custom layer. So if you're doing model development and you build your own new layer, we can support it through this extensibility on these devices. And then the 2 plugins at the bottom, the HDDL plugin is HDDL comes in, we call it 2 flavors, F for FPGA, and then the R is the Movidius one, or this, and it has multiple of these Myriad devices on the PCI Express card. So the Myriad plugins come as USB 3 sticks. The HDDL comes in different form factors of the same thing with multiple devices on there. So we've got a by 8, there's a by 3, and a by 2 from different vendors available. And then the GNA plugin is the Gaussian network accelerator for audio streaming. It's used in conjunction with the Caldi So there's, I mentioned earlier, there's a large number of pre-trained models and samples. So we've got, let's say, age and gender, eye level and high angle human detection. So for example, you've got a camera at a desk or a camera on a lamppost, different models for that. The license plate detection, it's specified number of pixels that you need to read. Effectively, the HTML data sheet that goes through the input requirements and output requirements, where it was trained, usually what the data set is. So you can go back and find the white paper and see how it was developed, and if you want to, effectively how you can retrain it or modify the model. It's a large number there. As you may have noticed, a fair number of them have come from the autonomous driving, assisted driving piece there. So, detecting pedestrians, bicycles, and other cars. Number of them in there for, I would say, face, head, emotion, pose, skeletal detection, and those are a bit more flexible. You can use those for, if we've got a smart classroom demo, for example, we've got them in the use case for a smart digital signage where it will detect user head pose to make sure they're actually looking at the signage and maybe what their age and gender is, so the ads on the digital signage can be tuned to the people that are actually. So these are pre-trained models. A number of them come with samples, but these are just the models themselves. And then we have samples, which are, I would call them, they're a bit further along in the application domain. So they're more complete. Now, you can generally download these, set it to the directory where the models are stored and run it. Where some of the other ones, no, you have to go and do a bit more work to do. So you can use them you can change the models out. So if you want to try different accuracies and things, you can do that. And we've got them there for object detection itself, just particular pieces on a photograph, or single shot detectors where we do bounding boxes, or segmentation where we do a bit more computing and be able to detect the outline of an object, for example. We've got a couple of more slides on that later. This is there's a quick overview of some of the benchmarks. With a large, more extensive range of benchmarks of the different models and everything. But this shows some of the models, for example, running on that, I was calling that 8-way HDDL card. So it says Intel Movidius VPUs, so that's the chip that's on there, and we've got 8 of them on there. So if we look, see if we can see my mouse here. Now, GoogleNet, for example, is running at 717 frames per second. Now, they've done this and said, okay, this is the effectively how many frames divided by the power used. Pretty much the same as this one, because they all use all would say nominally the same power. Certainly when you're running a benchmark, you tend to run the system as fast as it can go, so they're all topped out there. So there's different ways of looking at it. This final one here, right, is the frames per second divided by the thermal design power divided by the number of dollars to buy one of these cards. So this one, obviously, GoogleNet, if you're looking at that, that's get the best bang for the buck for the speed of all of these. Intel Media SDK, we mentioned that, a little bit more on that. Its support allows you to use what's branded as Intel Quick Sync Video. So it's got support for the hardware codecs on the chip that you're using. It will automatically detect them if they're not there. So you've designed it for an Atom, but you designed it for a core processor, but now you're using an Atom, and it hasn't got these all the codecs. It will fall back to doing this in software, so it makes it projects between different hardware. And then one final slide on the Intel integrated graphics. So the reason that we mention a lot about the Intel GPU is because there's basically one in every system that we ship. So your laptop that you're probably got right now, desktops, everything. There's about 2 or 3 Xeon server chips that don't come with a graphics built in these days. Graphics chip, but so basically what this points out is that you have a large section of your CPU or your processor core. In this instance, it looks about 40% that's dedicated to graphics. And if you're not using that to run a game, for example, then you can use it for OpenVINO. Offload the CPU, so offload the inference to this GPU, and gain substantial performance, and not only substantial performance, but gain more processor headroom. So you've and then you've got 3 out of these 4 cores available to run different applications. So generally speaking, you will need to dedicate one CPU core to shuttling the data back and forth from the Gen CPU. The other way to look at it is if you are using the Gen 9 CPU for graphics, say for an HDMI system or whatever, then you can run that same application on any of those CPU cores. There are APIs to pin inferences to particular CPU cores. There's a new API that's been developed called Multi that allows you to just say, okay, use everything you've got, and it will find the next free device and use that. So it will flip-flop between the Gen CPU and the Gen 9 GPU, CPU, and any other devices that you've got installed, and use the next free one for the inference. So an auto leveler or a system built into OpenVINO for that. See, this GT2 tends to be the Atom processors. GT3 and GT4 are branded as Intel Iris graphics, and then Intel Iris Pro. So you'll see those on they're on the NUC systems, for example, or on laptop processors. You'll see those in those. Basically, it's more and more of these execution units. So we start at 24 with the GT2, we go up to 72 execution units for the GT4. More parallel units, the more you can do in parallel. So that's generally you can figure out which processor or which GT4 you've got by going to there's an Intel website, arc.intel.com, that will break down all the bits and pieces from your processor to figure out what you've got in there. If you're making an embedded system and choosing a different processor, then you can also use that to figure out. So the graphics system uses, or the GPU uses OpenCL to develop the kernels for it. So we mentioned earlier OpenVX. So OpenVX is part of this controlled by the consortium Kronos consortium. And if you get a OpenVX certified device, then it will run any of the OpenVX kernels. So it's got there are slightly different levels of support, obviously different versions, but generally speaking, once you get yourself a OpenVX supported device, you can run into these the Kronos benchmarks. And how this works in the OpenVINO piece is we use data neural network, CLDNN, to support these, to use the sort of Kronos API and the OpenVX pieces to run the kernels. And we call a kernel. A kernel is akin to a layer within a model. So there's one particular kernel for ReLU. There's another kernel for the other types of layers within the model. And it's saved here. You can see under the distribution, we can create custom kernels that allow you to layer an unsupported layer or a custom layer in your model. We can use OpenCL to support those layers. And it says the other kernels, as you see them off to the left, other kernels and filters, those are OpenVX kernels that do things like color conversions, scaling, those sort of pieces. So they're optimized to run on the GPU hardware, these systems in parallel. So they're an accelerated version, effectively. A subset of OpenCV is what OpenVX will look like. So if you look at OpenVX, you can see that there's a comparison that shows you the support, the corresponding pieces in OpenCV. Let's see, next one. So this shows how a processor, or no, sorry, how an application is effectively developed using OpenVINO. So we start with a video on the left, road, and if you look on the right, you can see the car on the top has got a bounding box around it, so it's been detected. So what your application will have to do is decode the video stream coming in. We can use the CPU and the GPU for that to get one particular frame. We then use the OpenCV library, although we can use OpenVX, to do some pre-processing. And the pre-processing, there are certain standard ones, color space conversion, those sort of things that we've got ready-built library. That converts it. Some models, for example, require the image to be scaled to a particular size, 224 by 224 or 227 by 227 are fairly standard systems. You'll see those numbers pop up fairly often in source code. Once the model or the frame itself has been pre-processed, it's passed to the inference engine, and then at that point, the application program can decide to run across multiple engines or one particular one. Say we've got FPGA and VPU. The VPU / NCS are sort of the same model, same inference engine. There's just multiple VPUs in multiple NCS style chips in a VPU. So the inference block, if you see coming out of the bottom of the inference block, there's a section there about a trained model, which we've downloaded with the fixed constants. We run it through the model optimizer once. Intermediate representation, and those are given into the inference engine. So you need to do that once, or every time you change you bring in a new model. But you can run multiple inferences of the same thing. Once the inference is run, we use the OpenCV library or OpenVX again to do post-processing. And what that might do is take the output of the model and convert it into what we call human readable format. output an X and a Y location of object that's detected, and a label saying I detected object number type 3. So the OpenC library and the post-processing is used to make that human readable. So it will say, it will actually draw it on the screen, for example, and instead of saying label 3, it will say it's a car, things like that. And then if you want to recreate a video and save off the video or show it to somebody, you can use the Intel Media SDK to encode that video again. Now that last part is effectively only used if you've got somebody that wants to look at the video. If you're doing, I would call traditional computer vision, you would effectively stop there and take the data that the model has found and use that data directly. So for example, if you're counting the number of cars going through the street lights or traffic lights, you don't need a video, right? You just need a number of cars. If you're testing the application, you may want to create a video, count the cars manually. 12 cars going through, you can see there's around about 12 cars to validate the model. So that's why that's there. And the way we've set up our samples for OpenVINO, they generally are doing that so that you can see it's functioning correctly. But several of the samples also spit out the data in MQTT formats, for example, so they can be exported to a different system, either in the cloud or a different computer to take the data and process it. So there's a slight difference between the binary version, Intel distribution. It shows the pieces here. So on the left column here, we've got the Intel distribution and then the open source toolkit. You notice here the FPGA plugin is not available. The Movidius plugin for the Vision Accelerator is not supported, but the one for the neural compute stick is there. Other differences are there? Oh yeah, FPGA runtime environment. So the FPGA runtime environment is a piece that is loaded onto the FPGA itself. So it's binary put on. That's not available in the open source piece. It's physically programmed onto the FPGA when you get it from a vendor. And we don't have the OpenVX samples with Media SDK available. Okay. So before we move on to the model optimizer and inference engine, we'll do a quick stop and see if there are any questions on the overview. Shane, has been anything come up on the chat window or anything?
No question from the chat window.
Okay. Say I'll have a drink of my slightly cold coffee, and if people have got questions, you can either, as I say, put them in the chat window, or you can switch yourself off mute and ask the questions directly at this time. Sounds good. Okay. Well, either everybody understands everything or they don't understand anything, but we'll move on.
So are you going to have a slide on what the next release of Open R2?
No.
Okay, thanks.
And the reason for that is this is a public non-NDA presentation, and we don't talk about forward unreleased parts yet.
So I thought you said it was releasing today, so I didn't know if you'd be able to talk to it.
Yeah, so we'll get the public release today, and then we'll get trained on it, and we'll do all of our stuff, and in a couple of months, we'll be able to train other people on it.
Right,
so yeah, we do know what's coming. No, there are internal documents and everything, but generally, we wait until It's a bit. We wait for release 3.1. Put it that politely. When it comes out and hits the public, there's always, there's usually something that we doesn't quite make it. So if you may notice, if you go and look for release 2, it's actually release 2.1 that's available on the website. So because we're going out and teaching lots of people, we make and by tested and stable, I mean lots and lots of public people have used it. So the things that are different that I can talk about, there's really there's some more models. There's not much change this version coming out. It's fairly stable. There's some optimizations obviously and things like that, but we're hoping that it's not a big change from 2 to 3 because all of our training material is written for validate all of our samples and everything. And we've had.
Yeah, can you hear me?
Yeah, sure.
Hi, Stuart, this is Priyanka. So
Hi.
I just wanted to help you here with the question that what will be the new features in R3. So one thing you can definitely say, right now we can't share all the details because it's not publicly released, but you can say that there will be some network loading optimization so that the network will be loaded quicker to reduce the inference time. And another thing is there will be new command line which can help you to minimize your runtime package so that you can have a smaller footprint of your runtime package which you can deploy on your deployment hardware.
Okay, yeah, that's true. Yeah. So what that allows you to do is, what it will do is you develop your system on, say, a decent laptop running Ubuntu, but you want to deploy it on a smaller system with a much smaller disk, less hardware. Instead of having to install the whole OpenVINO, the Open and install copy all the files into an installer, you can then move that bundle over, untar it. I don't even think you have to. I think you may have to run one setup file, and it will bring across all the model that you've developed and all the code, and let you run it without doing the big download and install that you would do for the development. I think that's going to be out as a preview for Linux. As that one.
Yeah. The XML file of the intermediate representation is pretty easy to work out and see. The bin file, though, what are the constituents and the special magic in the bin file?
Really, there's nothing much to it. It's the trained constants. So if you've got a model that's being trained, all right, the things that change is not the model itself, but the actual constant, whatever constants, the variables. So the how much do you model? All of those are the things that are tweaked by the training, and then once they're locked down, they then become constants, and we call it a binary file, but actually, I suppose it is a binary file. These are then the constants that are loaded in per layer.
Presumably, it's in some way compressed because there must be a massive number of weights and biases and the like.
It's not actually that big. No, it's not, and I don't think it really is compressed much. Because we'll have one number, right? So that's it's one of those. No, the piece will be the bit you can check, and I suppose you can check it if you want. Really, is we support different sizes of models. So we've got the FP30 floating point 32, floating point 16, and 8. We can check and see what the difference is between an FP32 and an FP16. Hopefully it's half on the binary file, right?
I know that'll be interesting to see.
It's really not big. The models tend to be fairly small once they've been certainly once they've been run through the model optimizer. That's the whole point of it, is making it small so we can load it quicker.
Mm-hmm.
So there are pieces moved out of it, sections deleted. I don't think they do much with the constants.
Sure. So I mean, sparsity and near or actual zero weights are going to be reflected in the bin come what may. So if we're going to deal with sparsity, that's going to be down at later on. Yeah.
I think it'll be done by the model optimizer. It will take things like that out. So there's no. Yeah, because it will do a lot of combination, and a lot of the combinations will be will take out some of these constants. So we've got an example as we go through onto the next slide. Actually, we might as well just go and have a quick look at it. So the model optimizer. Yeah. Any other questions before we go? No? Okay, so we've seen the slide already. As Peter said, there's a binary and an XML file. And then that's loaded into used by a C or a Python program. And we've got some examples of that that we'll get set up and show you those. And then it sends it to one or more of the plugins. This is the sort of things that the model optimizer will do. It pulls models in from various frameworks. If you have a look at the directory, there's a Caffe directory, there's a TensorFlow, there's MXNet, all of these, and a lot of the layers. In fact, almost all of the layers, there's a little file for those, little Python program that, because the Caffe reload layer is somewhat different than the TensorFlow reload layer, so there's a separate one for each model framework. Say we validated over 100 models. I think it's over 140 now. And all the public models on the ONNX Model Zoo are supported at the time of the release. It's changing, so we validated it 2 weeks ago when we locked down version 3.1. So if something's come out in the past 2 weeks, buyer beware. So the things that the model optimizer does, effectively quantize. So the quantized pieces, if you've got an FP32 model but you want to run it on an FP16 device, we can do those sort of changes. There's more details or more complicated thing if you want to do an int 8. So help revalidate the model, check the accuracy, or change the accuracy, get some accuracy back than just sort of chopping off the extra bits. The intermediate files, the IR files, don't require the framework if we support those layers. But if we don't support that layer, you can fall back to the original framework. So if you're developing your own model in Caffe, it's not supported, we can use the original model or the original layer from that model in Caffe. We obviously can't do that with models that we don't have the source for, but if you're doing your own development, we can do those. Or if I change the slide, yes. So this has been updated. Good. So The CPU supports floating point 32, floating point 16, and int 8 models. The and 32, but it's recommended for 60. It runs better. The mirrored device, the NCS, is a fixed device. It's so it only supports FP16, and then the FPGA, although it's totally programmable, the bit streams that we ship are have FP16 and FP11 hardware support built in. So I mean, there's a 32-bit DSP in the FPGA. There's multiple, but the bit streams have been optimized to use FP16. If you want to rebuild your own FPGA and support FP12 in a bit, well, actually 12, FP12, you can do that because the FPGA is programmable, but no, you're on your own. So the bit streams that we ship have these 11 and 16-bit. The 11's the sweet spot. That's what we found. So things it can do when it does the optimization, node merging and horizontal fusion and all of those things, drop unused layers, so we can do those bits. If there's, we can add those in at conversion time or scale, multiply everything at conversion time. So that's not done, it's done once rather than every time we infer a model or infer a frame. I think the next one, yeah, this one's got some of the pieces there. So this one here, batch norm and scale shifts decomposition. So if you look at number one there are 4 constants. There's a multiply, there's an add constant, there's another multiply, and another add sequence, another add constant. By one add. So straight away we've got rid of half of those constants. So not only do we make the model smaller, the binary constants will be smaller as well. They won't need so many. There's an example on the right of that BN and scale that have been scrunched down, so you can see what was there's at the top 64 channels, 112 of 112 coming in, and a 256 channel, or two 256 channels coming out. This is the equivalent in once we've merged it. So that's the ResNet 269 block from Cafe. The piece there says from Netscope. Netscope is a this thing. So this diagram itself has been drawn by Netscope. So if you want to actually have a look at an XML file and see it in human readable format, the Netscope tool is a great tool for that. Now we've built that into the DL workbench. So if you use our workbench and you run it through, you can use this tool that's built in. It will draw a diagram. And the nice thing about the diagram, we can't see it here on the screen, is now if you move your cursor over this system here, you can actually see the constants. It will pop up a little window and show you a bit more. So it's it's interesting to people that know what a model is. So it's one of those sort of things. I beg your pardon. A lot of people are just like, okay, press the button. Out comes the magic XML and binary file. But for other people, it's like, what did it do? Did it break my model? Things like that. So if people are developing a model or have trained a model, then they're interested in seeing what the model optimizer has done. So this is another way of looking at those things. So where we're taking that, actually we're taking the convolution and the batch normalization and combining those, and then the compilation and ReLU are when they run the inference, they're effectively loaded into one optimized kernel. So there's still 2 separate operations, but it's one kernel, one OpenVX, or one small piece of code that runs both of those pieces there. So instead of what would be 3 operations, convolution, get the data, send the data to the batch, none of that. The data, send it to the ReLU, and then take that answer and send it to pooling. We can now do one load and one store. So not only have we shrunk down the number of constants, we've also stopped the data shuttle back and forth. So there's multiple ways that the system is optimized. Other things you could do. Where's my mouse gone? There we go. So you could cut off parts of a model, and the reason you want to do that, there are various reasons to do that. I mean, obviously, if it's too big to fit, then you need to chop it down. So, for example, the NCS chips or the Movidius chips within the NCS devices are fixed size, whereas now CPU you just still fixed size, but you can actually spin something out to disk if you really want to. But these CPUs can use a much bigger model than the NCS chips, which I think have got 4 gigabytes of RAM on board. And we've found one system, one sample we've got where we're loading multiple models where we run out of space on the NCS device. I can't remember which one it was, but generally speaking, all of the models that we've got and all the stuff and samples we've got will run across all the devices. But if you make a bigger model, you can chop it into 2 pieces and run it across multiple devices. If you've got these pre or post processing parts, right, you can take those out. So, for example, we recommend the last layer on a lot of models than it does on an FPGA. So the models or the examples we've got for FPGAs do that. So they'll specify a different layer as the output, and they use that using this command line options. You can effectively take a different layer of the model and specify it as an input. So if you and multiple ones if you want, really. So if you want to do more pre-processing, you could use this and then take that pre-processed piece and send it there. So if you're some of the reasons for that is, say you want to debug that layer, right? You specifically want to, okay, now run that layer on the CPU, run the rest on the FPGA. You can chop it, run the second part on the FPGA, and run the software debugger on the first or second layers, and get more data on whether it's working correctly or if there's something you want to optimize within it. And similar to the output model, effectively before the inference is completely finished, you can get a new exit point and run that layer on a different device. And we use that sort of method effectively to run things like unsupported layers. Now you've got a layer that just won't run on the FPGA because it's not supported. You could chop the model up manually and run the unsupported layer on the CPU or the GPU. We do that automatically for you if that's what you want to be done with some of the flags. Tweak it. All of these options are available. This is the bin and the XML file. So this is the XML file. I don't know if you can see it on the screen. Depends on how you look. But if you look, for example, at this input parameter shape, which is dimension 1, 3 colors, X and Y, 227 pixels by 227 pixels. That's what that means there, right? where does it fit? There is where it. Click too far. There's the corresponding part, I think. No, here we go. Dimension 227, 227. So there's the corresponding part in the XML file. So there's, for some things, right, there's obviously a one-to-one correspondence. Now, if we're getting rid of a couple of layers, they're not going to be in the XML file. But if you want to see what's been done to your file, you can read this XML. But I would recommend using a graphical tool, and it will just show you the picture of the layer and the parameters. Shane, I don't think we do have a model. Or are you going to do it?
We can leave it to the DevCloud.
Yeah. Okay. So yeah. So basically, in our face-to-face labs, this is where you would be doing it. So there's a couple of command lines: download the model, convert the CAFE model to the XML data type. By default, it's FP32, and you can choose things. You can run the same one and get an FP32 and an FP16 model as well. We've got models in the cloud that will you can concatenate them together with the system. I think the car security barrier, demo security barrier will automatically do the scaling from one format to the other. So as you move from one model and take the model output from one model and put it into the other, do the scale conversion for you. Okay, so Inference Engine. Let's see, same slides as I said before. All right. So Inference Engine, it's got one API for one entrance piece to all of the inference engines. We call it just it tends to be called just the inference engine, but really we've got let's see there, we've got 5. I would say, I'll tell you which one's the extra half. So on the left hand, FPGA plugin, starting underneath the Inference Engine Common API, we've got an FPGA plugin, a math kernel library plugin, CLDNN plugin, the Myriad/HDDL plugin, that's the half, all right, and then the GNA, the Gaussian network. And then you go further down, the FPGA plugin is built using DLA. So, help me here, Sean. Deep Learning Accelerator. Yeah, I think it's just things like that. These sections are broken into intrinsics. So we're using the math kernel library is I would say hand optimized in some way, set of CPU optimized CPU. Exactly, whatever that was. The OpenCL DNN CLDNN plugin is written OpenCL, we mentioned, for the graphics processor. Moving on to the Myriad, the Movidius API, and it targets the Intel NCES, Intel NCS2, which is the version 1 and the version 2 of the neural compute stick. And then the same one supports the HDDL-R devices. So those come in by 8, by 2, by 3. I think they even come in a by 1 PCI Express, mini PCI Express device. So you can plug it into effectively a wireless slot. They've also got them in the M2 format, and then by 8. plug-in card for like a server style system. And then the GNA uses the GNA API. That uses different hardware. It's effectively, in some ways, a device for making something similar to an Amazon Alexa or an Echo or a Google home device, where it can decode streaming audio. So it's somewhat different than these devices, which take all of these other devices take a process at one at a time, whereas obviously if you're doing streaming audio, there's no end. But also you don't need to wait until it ends to start. So different format, different style of programming for using the audio pieces. So the heterogeneity support allows us to execute across different or multiple devices. We've got an asynchronous API, which allows us to kick off an inference, and now it's non-blocking. So we can come back and start reading. And we can also post-process the previous frame, so our previous results, while the inference is taking place. So it speeds up the overall frame rate. The FPGAs, so the same system. We've got some of the new Whiskey Lake boards in. It runs. We drop it on there. Install Ubuntu with OpenVINO, and boop, new processor support. So it gives you some future. Let's see. Next slide is a bit more on a workflow. So I think we talked about that before. We convert the model, we load a plugin, read the model in IR format, so the XML and the bin format. Once we've read that, then we know what size the input and output should be. We can actually ask the model. There's APIs to ask the model what size is it requesting, and we can convert it. So when you read in, you can read in a different model, and your model code here in section 3 can convert to the size the model requires. We then load the model itself to the device. A CPU, there's not really a load piece, but for the graphics device, for the Movidius devices or any of the FPGA devices, no, they are loaded over a USB or a PCI bus. We prepare the input, which is effectively convert it to the right size if necessary, and run the inference. And then for every frame, we run through this inference loop. And we process the output if necessary to either recreate a video or send the results of that inference to the another computer to act upon. Change the traffic lights. There's lots of cars coming, things like that. So we talked about pre-processing. This is an example of the pre-processing. Cameras, anybody who's done any photo editing, each pixel, occasionally a transparent byte. And all of the models that are developed, instead of going pixel RGB, next pixel RGB, they want all of the red pixels, all of the green pixels, and all of the blue pixels in an array. And that's the format they're expecting. So generally speaking, if you take a photograph from a camera, you need to convert it. Now, the easiest way is to copy the code in the samples that's doing it already. There's a couple of for loops, and it will do it to C++, and we've got it in Python, but even the Python one uses the C++ Python library. So So this is just an example of sort of pre-processing. As again, if you're needing to scale images, that's done as well. Although there are options now to scale images using the inference engine. So we can send in a HD image, it will rescale it within the inference engine. The advantage is it's easy. The disadvantage is you're sending an HD image, so 1920 by 1080p over a bus. USB or a PCI bus, you're using, it may take longer. Well, it will take longer. Whereas if you do the scaling before you send the data, you're sending a 300 pixel by 300 pixel image to the inference engine. So ease of use versus a bit of optimization there. So post-processing, developers are responsible. There we go. So every model, almost every model we've seen comes out with a different output format. No, they're somewhat similar in some instances. So a simple classification similar to AlexNet. It will output, the answer will be an array of confidence scores in the floating point. And the number of elements in the array are the number of elements in the model. So if it can detect 20 objects, for every frame, it's going to send you an array saying, this is what I've detected in that frame. If it's a picture of a car, it will hopefully be 90% this is a car and 5% this is a dog or a horse, depending on the model. But it will send you the confidence, hopefully very low confidence, of things that are not in that image. So it's up to the developer to figure out, okay, what threshold's good enough for me? Does it have to be above 60% before I say, there, that's the car? And do I throw away the others? Or do I pick the top two and say, I think it's a peach, but it might be an apple, right? There may be some, things like that. So development. And then the SSD one, the single shot detector, what that returns is for every object that's been detected, there's effectively a box. There'll be a tuple or whatever with a confidence score, a label for that item that's detected. There will generally be a label number. So if you've got 20 objects, it will be, okay, I've detected object number 3. And then the X and Y locations, basically top left and bottom right or whatever, 2 corners. And that can be used to either draw the bounding box on the frame. So you can actually draw a picture around the car, for example. Or it may just be, okay, let me find the centroid of that X and Y centroid of that box. I can use that as the target for, it's my robot having to aim for that device. So I can now know where that is in the picture. So I can now move the robot or whatever. You do need a well-documented some are not as well documented. Some of them you have to look through the source code of the app that comes with it to figure out what they are. Okay. So we're going to have a quick break, which means I get to go and get more coffee. Shane, I don't know if you want to put up the DevCloud access at this time.
Okay. So we can have attendees to register for DevCloud at now, right?
Yeah, I think so.
Okay.
And then I can have a break and they can keep working, or at least so that when we get to it, we can do that.
Okay, let me bring up my slides. Yeah.
Do I need to stop sharing or can you override?
Yeah, I can do that. No worries.
Okay.
Okay. Now everybody should see my screen now, right?
Yeah, I'm seeing it. Yeah.
Okay. Like, no, I only have one screen. Download for webinar. Okay, so people are asking where to download those slides here. I cannot see myself. It's kind of got lost in the chat window. Oh, it's here. Okay.
Yeah, we got a gray screen. I don't see. I see your cursor moving around, but nothing much else.
Okay.
That's better.
Paste a link in the chat window. For this open window, the slides we're using here, we kind of compressed several different slides into one. So this is called open window in 2 hours. But if you want to read more, the place I put in from the GitHub, that's the normal workshop we do for 2 days, and you can find all the different slides. There's more information in there. All right, let me close this. Okay, so while Stuart was taking a break, so let's talk about the DevCloud for the Edge. All right. Okay, so like Stuart said, DevCloud is a cloud for the developers to test out all the different inference. So basically, this is how it works. So you are getting access to the DevCloud through the HTTP on your browser. So it's basically a Jupyter Notebook portal. So, once you have access to that, when you open that, you go to a Jupyter Notebook platform, and then you can choose what there's the Python examples you can run. There's the C++ samples you can run. You just pick whatever you like to run the samples. And once you do the inference, it will create some job queues and send it to the different them to have done the inference and sending back the result. And then the result will appear on your screen on the browser. That's basically how DevCloud works. So there are several different set of devices using Xeon CPU, Core i7, i5 CPU, and there's also FPGA card installed on some industrial PC. There's Inference accelerators with VPU. Yeah, several different set of devices. All right. So the main benefits of using DevCloud is software before you making the decision which one you like, and you can making the comparison between different platforms to see to choose the best performance matches your need. So let's get that. And this is not the right information. Let me put it here. So today is October. So this is our code. All right. Okay. So everybody can go to this link, and let me paste this for registering. Chat. Okay. Yeah, so I'm pasting the link in the chat window, so everybody can go to this link and register your access to the DevCloud. And while you are registering that, it will asking you for the passcode for today's events. So the passcode is shown on the screen now. So that's the one, and this passcode is valid valid for 3 days, but once you have the access to DevCloud, it will give you 7 days access to the DevCloud. You can uploading or downloading your application onto the DevCloud and try your own application. Let me show my web browser. Okay. Okay, once you click the link, I think everybody can see my web browser now, right? And you will go to this page and you will put your name, organization, email address, and professional email address. Otherwise, you probably won't see won't receive the back. So let me paste the passcode in the chat window as well. Okay, so that's the passcode. I already put it in the chat window. And here's the place you put your passcode. If you don't receive a email confirming back, I think after you click submit, there's a button or link on the page showing it says you can go into the DevCloud directly. And for yeah, I don't remember, but it gives you the link to get access to that, even though you don't receive the confirmation email.
Yeah, it's like it says, please go to the waiting room.
Okay.
Yeah, and it will start up the server. And actually, no, I think it's just doing the registration of that.
So you don't have to really waiting for that.
Yeah, so that's why if we figure we can get that started, it generally takes 2 or 3 minutes. It's not long, but if you get that started, well, we'll do a couple of quick slides on the NCS2. I should really get Peter Logan to do the NCS2 slides.
Oh, he's from VMC.
He's
Okay.
the program manager for the NCS2 right now.
Oh, okay. Cool. Yeah. So once you have done the registration, in that way we can know, or maybe story can go on and people will continue getting the confirmation email, right?
Yeah, I'll just continue on, and then once we get to, we've got like 3 more little presentations, one on the Movidius, one on FPGA, and the one we call the heterogeneous plugin. Actually, let me just pick the agenda back up.
Yeah, Stuart. There's beer tokens in it if you give us a
mention.
a nice speech or.
I'll be in York in a week and a half, so I'll take you up on
that. York as in Yorkshire.
Yeah.
Oh, yeah. You were saying, yeah.
Yeah.
Absolutely.
So those beer tokens valid in York? No, that's what I need to know. No.
I know some stunning places we could drink in York.
All right, sounds good. Let's see if we're going to share. Let's see what we get. So can you see the agenda now?
Yes.
Okay. So, let's say we've got. This is my life from Peter Logan. Is the Intel Movidius one. FPGA Inference Accelerator. We'll cover that, and then once you've gone through some of the examples and you're getting to the next stage, you think, oh, I want to try something a bit more. Then there's heterogeneous plugin, async API, and multiple models. You will be running those, generally speaking, in the DevCloud, but this will give you the backgrounds to what you're doing when you're running them in the DevCloud. So let's just move on, and then if people haven't managed to we can sort it out at that time. Okay, so wrong click. Here we go again. There we go. Intel Movidius Neural Compute Stick 2. This is where it gets somewhat confusing. So in the Neural Compute Stick 2, there's a Myriad X vision processing unit. And in the Myriad Compute Stick 1, there's a Myriad 2 vision processing unit. The two are still available. The Neural Compute Stick's the one that we obviously recommend. It's the bestest, fastest. The price has just been reduced, I think, in the last month or so. It's like $69 retail. It supports all of the frameworks, not just TensorFlow and Caffe. We've got a slide there, slightly out of date. So all of the frameworks that are supported by OpenVINO will run on this system here. It's a USB 3 device. So you need to get best performance. You can plug it into a USB 2 Raspberry Pi and run on Raspberry Pi. It runs faster on the new Raspberry Pi 4 because it's got the USB 3 Type A on there. So that's what we recommend. It will work on a USB 2 system, so that's fine. Actually, the way USB 3 devices work, they power up a USB 2 device and they run a little program that downloads the USB 3 driver and then they reboot. So that's why it's supported on USB 2. The dimensions are, you can see there, it's slightly wider than your usual USB stick. So you'll have fun plugging two of them together on a laptop, which is why we recommend using a hub. They're a USB 3 hub would be good if you want to plug in multiple devices, which you can do. There's code out there for running parallel inferences on one device and the second inference on another, so separate models. Run two models on the same device. There's not a problem there. And the same operating systems. Actually, that's one of the changes that we can say about Windows OpenVINO 3. The release coming out, I think it's tomorrow. I'll let you check with Priyanka. I think it was 1st of October or today. It supports the Neural Compute Stick on Macintosh now. So you can plug that into your Mac and run that there. Let's see. So there's the difference between NCS1 and NCS2. And this is what's inside that device. So we're using the Neural Compute Engine. And then we mentioned that you can extend it. So you can add more support for different pieces now. And those would run on the Shave cores, which would run the OpenCL kernels. The NCS2 device, the Movidius chip that's inside it, this is what we're showing here, also has a PCI Express interface, and there are some devices just being brought out that have a native PCI Express device connecting available, whereas all the previous devices used a PCI Express to USB conversion chip. So some of the newer ones, I think I've seen one or two of the newer ones that have native PCI Express. Well, mini PCI because they're tiny. Let's see. This is the supported layers for Movidius for OpenVINO 2. And you can see the ones that are highlighted in yellow are the newer ones that came out. So we, like the FPGA, we support more layers as we move up the food chain with OpenVINO. The best way to find out really is to have a look at the latest documentation. There's a link there that shows. Actually, let's see if the link. Yeah, there you go. There's a link with all documentation. It shows all the supported layers for all of the different devices. The reason you need to know that is, or not the reason you need to know it, is to get around the problem that we have with this, right? We don't support new layers or whatever. There's two things. You can extend it yourself, or you can find a device that does support it, and you can run that particular layer or layers on the other device. So generally speaking, the CPU supports. That's it. So we'll skip the demo because we'll be running that on the DevCloud. Unless you want to run it, Shane, have you got one that you're running on, or are we running behind time?
I think we're fine. It's 9:50, right?
Yep. So we'll just keep going, and we can run the examples later. Okay, sounds good. Coffee's too hot. There we go. All right. So FPGA. Any questions on the NCS2? Okay. One thing that is available, let's see, you do get a version of OpenVINO for the Raspberry Pi. There's an installation candidate. It's slightly different than the other ones, but there's a complete set of documentation on how to get up and running and installed on a Raspberry Pi. The Python code, actually all the samples and everything. So the pre-processing, post-processing runs on the Pi. Runs on the NCS2. So unlike like an Intel processor, you can't run any inference on an ARM processor. You have to run all the inference on the NCS2. So some slightly different model than plugging a device into an Intel processor laptop, for example, or an Intel Linux box. But generally speaking, no. Anything I've not found any problems running all of the models that we've got on the inference stick plugged into the Pi. It will run as an accelerator for a Raspberry Pi, and there's some benchmarks out there. I'll put some links up when we're running the DevCloud. There's some pretty decent stuff up on GitHub people have done. Some Intel innovators have developed some examples for that. The FPGA is next. So let's see. So the field's programmable gate array. It's what FPGA stands for. It has, as I say, millions of logic elements, right? Thousands of memory blocks. So the biggest advantage, at least for OpenVINO, is the things it can do in parallel, because it's got thousands of these devices. So if it's similar in some ways to using a GPU, in that you've got multiple little execution units. You can set up your FPGA to be a device like that. You can, what do you call it? You can. The difference between the GPUs and the FPGAs is the FPGAs are reprogrammable to tune it. So if you want more memory, or you want more DSP, or you want more cache to store a larger image, the memory blocks, you can do that. So you can do a little bit of tuning and trade-offs depending on your application. There's it's nicely set up with Quartus FPGA development tools. There's basically a tuning sort of file that you set up, run it through there, and it will reprogram all of the elements. So no RTLs required. Actually, very little. If you just want to move around the various blocks or change the different sizes of the areas there. The card that we support is this Vision Accelerator design, so this VAD card. We've I think there's a range of them out now, but the one that we've been using is the Mustang F100 from IEI. That's the one that'll be in the cloud, the DevCloud on the hardware boxes. It's a fairly large system, large networks, up to 4 billion parameters. 24/7, 365 operation. I've yet to find a processor that switches off on a Monday or a Tuesday, but seemingly the FPGAs may, but these ones don't. This is a 24/7, 365 operation device, which is good to know. And it's got extended lifespan. These things are going to be available for 8 to 10 years. So, so it's because of the part of IOTG, which is Intel's IoT group, long life support. So let's rearranged it. It was scrambled when it first came in. So this shows the improvements in the FPGA performance from a long time ago, before OpenVINO was even called OpenVINO. So the left column, CVSDK, was what OpenVINO was called before it was branded. So there were beta releases, March 18, and at that point, ResNet 50 was at 31 frames per second, and ResNet 101 was at 27 frames per second on the FPGA. Year over year, right, we've got a 9x speed up on the same model on ResNet 50 and a 6x KNAPX speed up on the ResNet 101. So no changes to the application code, no changes to the model. You did have to run it through the new model optimizer when you get to release 1, but that was basically what was required. You would probably be using a newer bit stream, all right? But those bit streams are supplied with the system. We've got an extra, we're now at 200 FPS on ResNet 101 and 450 on ResNet 50. So the FPGAs obviously continue to improve. New algorithms come out for, so one of the typical ones, or the fastest ones, was Winograd, which is a multiplication algorithm. And I'm pretty sure that was the one that was implemented between R2 and OpenVINO R5 in 2018, because Winograd gives you a 2x speed up in multiplication, and that thing seemed to be double. So when new algorithms come out, we'll implement those, and you get the benefits of those basically, for free. Just run the latest version of OpenVINO. So the FPGAs are broken up into this sort of architecture. The feature map cache, that's where the image is loaded. It's double buffered, so you can have one image in there that's being processed and another one being loaded in from the DDR into the feature map. So obviously that speeds up your loading because you have a preloaded image. The convolution PE array, that's doing the actual the math convolution pieces there. And the crossbar, down below the crossbar, you see these prim. So these are primitives. So those are ReLU, convolution itself, all of these. And what the system does is selects as many of those as are required for the model, or rather than the user does. So if you've got, say you need, you would shrink down effectively the convolution P array, add more primitives into the below the crossbar, and tune the model that way. Now we've done that with a bunch of bit streams. So it's we've got what we think are fairly well customized pieces. So you can go and choose a beg your pardon, you can choose a bit stream that's been optimized for, say, AlexaNet, GoogleNet, and SqueezeNet, or wherever. And basically, the way they're blocked is because they are. So I may be making that up, but if you actually look at the bitstream directory, comes with OpenVINO. It's got the names of the models that this bitstream's been selected to run well on, and there are 2 or 3. So there's some trade-offs between different ones. Some may use bigger models, some may be more accurate. We have them in FP16, we have them in FP11 available. They're field programmable, which means you switch the system off, it's gone. But there is a flag system in the FPGA, so you can actually hard program it. Not hard program, but program it to stay there. So that next time you power it up, it will reboot itself from the onboard flash, and you can just run again. So if you're deploying the system in the field, you don't need to load the bitstream from your laptop at that time. And then again, if you're wanting to use custom primitives, you can do that. So it's a method similar to generating custom primitives for the GPU. You need an OpenCL piece, but you're not using RTL or Verilog to program it. So much higher level programmable capability there, and we have a separate class on doing that. If you're interested in doing that, let us know. I'm pretty sure it's available publicly. I know the GPU one is. It's part of our 2-day workshop. Support the FPGA now, so that's available. Let's see. You probably remember this slide, but down on the bottom right, that's where the FPGA is supported. It comes, as I say, it's only available for Linux this time. The runtime environment does change between releases of OpenVINO. So if you've got a system and you've got OpenVINO 2 and you go get OpenVINO T3, you will need to upgrade the runtime environment. And that's done with a small JTAG device. And then the bit streams are just loaded over the PCI Express bus. So I think of it as similar to, if you're familiar with an Arduino board, you get a bare Atmel chip. It doesn't run Arduino sketches, but if you program it with the Arduino bootloader, then you can write sketches and they will be downloaded by the bootloader and run. So this is akin to the runtime environment is the bootloader, and then the bit streams are the programs that are downloaded and run at runtime. So in a lot of ways, the examples we've got on the DevCloud, there's one extra line in the code when we select the bits, select the inference engine for the FPGA. There's a line that says, okay, what bit stream do you load in? And it's called the AOCX. Let's see, it's got the historical name. It's the Altera Open something format. So it's still got some of the old Altera names, even though it's now an Intel product. There are 2 flavors, effectively. as far as an application piece is concerned, it's somewhat transparent. But if you're looking at the acceleration stack platform solution, it's more of a Xeon server, possibly in the cloud, those sort of pieces there. So it uses what we call the Intel Programmable Acceleration Card, and that's complete things branded as an Intel FPGA Acceleration Hub. And then the edge computing solution, which is the one that we're talking about here with the Movidius, stand card, and the one we'll be using in our cloud is the Intel Vision Accelerator design product. So you'll see that as Intel VAD. Let's see, I think the difference, if you look in the details, just above the Intel CPU, you can see an OpenCL BSP driver. And on the Intel Xeon, just above it, it's got the acceleration stack. And effectively, that's the difference. The OpenCL BSP is on the Mustang card, and the FPGA interface manager is on the programmable acceleration card. But above, you can literally write the same application. It will work across any of these systems. So this is what we've talked about before, where you take your network, interdistribution, you run it through the into the Xeon, you get a bitstream library is the slight difference, right? And you program it onto your system there. So the bitstream library, the one line there on is the one difference. If you want to do extensions, down at the bottom left, you go and find an IP architect. They will design it for you. That will allow you to customize this DLA suite, the source code. You compile it, and then using the Intel FPGA SDK for OpenCL, and you will get a new bitstream that can be loaded onto the devices. I'd say there's no need, if you're just wanting to tweak it and try a different ratio of sizes of extra primitives, move some primitives out, make a bigger memory cache, add more different devices. That could be done. You still have to compile it, but it's done at a command line, so it's not. There's no need to go back all the way to the IP architect and get them to design. If you just want to tweak existing pieces, the IP architect is required if you're using custom layers. They need to be able to implement the architecture for the custom layer in using the Quartus toolset there.
So is this DLA suite source code, is that coming from the open? Where do you get that?
No, it's a separate piece. So it comes effectively from the Altera team. So it's part of, I'm not sure if it's part of Quartus now. I need to check on that one. DLA source code, DLA suite source code. Yeah, I'll need to check on that. I don't really know. Let somebody online run it. No, they're not going to say. Okay. Yeah, I don't know. We can check. We've got a guy on our team, Carl, who's just moved over from the FPGA piece, but he's currently in Taipei teaching a class there, so can't quite ask him at the moment, but he'll know exactly where that is. These, in fact, are his slides. So this goes a bit more into how these FPGA works. Not stream buffer, a streamflow architecture. So if you look at the bottom right, there's the stream buffer, which is where we keep the answers and the output and the input of these convolution, reload, norm, and max pool loop. And up above that, you can see there's a crossbar, and then there's these reload, norm, max pool, are these primitives that we talked about earlier. And to say that you can move the size around, the optimization. The way it works is, we'll go through a quick example here. This is a LexNet, because it's nice and simple, and it has, in effect, 5 layers, or 5 different types of layers. So there's a convolution, there's the reload activation layer, there's the normalization layer, a max pool, and then there's a fully connected layer. One of those, actually 3 of those at the end. So if you look on the graph, the whole, can you see my cursor on the screen? Hopefully. This first section here, if I click on it, it's going to go away. Yeah, I told you. Let me unclick. Okay, so the first 4 blocks on the left, from the left to the right, has a convolution, a ReLU, a norm, and a max pool, and then there's the same again. So for these first 2 sets of that, all of these blocks below will be used. For the next one, which is like, there are 3 blocks that just do a convolution and a ReLU, and then convolution and a ReLU, and then convolution and a ReLU with a max pool. So what we do is we use the same piece of hardware. We load in different constants, but these primitives stay the same, and we bypass the norm piece for the first 2, and we bypass the max pool. So as I say, the runtime configurable and bypassable. So this data goes round and around this loop graph, and it's running. No, it's in hardware. And then when it gets to the last 3, you can notice that the block changes. It's no longer got this little outline. It becomes fully connected. They flip a switch and do a fully connected to convert the convolution block into this fully connected. So we run through 3 of those with a couple of reloads, and out at the back end comes this fully connected piece. So this is what we call this flow graph that's used. So this is the method that's running. So you can add in extra primitives, you can subtract primitives, and if they're not required by the model you're using, for example, and get more mathematical areas or add more area for the images coming in. Depending on which model you're using, as I say, there are a large number of bit streams. If you see on the right, this is the directory listing from OpenVINO, and the PL1 is the Mustang board. So 2019 release got let's see, 1, 2, 3, 4, 5, 6, 7 floating point 11 bit streams, and then 1, 2, 3, 4, 4 FP16. I think it falls off the bottom. And then the names, the LexNet or the GoogleNet or the MobileNet Cafe, these are the what we call fully supported models. So these have all of the primitives in that bit stream that are required by that model. So no, it will execute on the FPGA. A bit more thing. So I think the next slide has got like a bit, breaks it down. These are the networks and primitive supports on the back end. And this is actually the command line. So you'll see this command line in the DevCloud, in the C or the Python program. AOCL, and then want to program it, we program the AC10 board, and then this is the bitstream, the 2019 R1 P11. So it's a simple method to do that. And this slide here has the supported primitives and topologies. I think this again is release 1. All of these topologies can be built out of all of these primitives. How it works. So every one of these can be built. But if you go and find a model, which is easy enough to do, that doesn't have some of these primitives, then that particular layer won't run on the FPGA. And we show in the next section how we can overcome that problem. So this one here just shows you a bit more about the different topologies, the different frameworks. So the one on the left has got 3 primitives: the reload, the norm, and the max pool. Primitive execution array. And then the one on the right, we've got more primitives, so take up more space. So we've added, yeah, we're going up to 8. Is it? 9. Yeah, 9 primitives. I can't count. Yeah, 9 primitives. So the convolution array is smaller. No, so those are the trade-offs you got to do. And there are the feature map cache can also be, the size of that can be tweaked as well. So you can do a variation between the convolution feature map cache is where we store the image, and you can see that on this one where we've made the number of images that could be loaded in at a time, for example. So if you want to batch multiple images, you could maybe might be better with one of these sort of things. So we mentioned before that if a layer is not supported by the FPGA, what happens, right? So we've got this project plugin. So it allows you to take one network and run it across multiple devices. Now it will cause data to be shuttled back and forth between the devices. So if it's an FPGA, for example, it's going across the PCI bus, but it does allow you to execute it. So it's like, will it work at all, or no, it's not going to work. The other reason for using it is, you want to debug a particular but accelerate specific layers on an FPGA because they'll run a lot faster there. You could do that. There's 2 sort of ways you can do it. You can do it automatically. Someone's in the cafeteria. Yeah. So you can set it to do it automatically, or there's some flags you can use to override, say, automatic or manual mode. So so this is the automatic using the fallback policy. So we're saying, okay, run everything we can. If you say there's the hetero myriad CPU section highlighted, we're saying run everything you can on the myriad, and the pieces that can't run on the myriad run on the CPU. It's say what they call a greedy behavior, so it will try as best it can to run it on the myriad, and then fall back to the CPU if it can't be done. And the code, literally, no, we generally do it on the command line, but if you go and look at the code, it's the dispatcher get plugin by device, no, hetero, myriad, and CPU. If you do hetero FPGA, CPU, it does that. No, you can do CPU, GPU, right? We've got different examples that you can use. It only makes sense if you've got a model that doesn't run on the myriad, right? If you've got something that always runs on the myriad, it will all run on the myriad, and the CPU will never be used. Now, if you particular layer, you cannot, it's not working, or the numbers are coming back and it's not quite right. And you're like, I need to know what's happening here, right? If it's running on the Myriad, or if it's running on the FPGA, you're somewhat out of luck, right? There's no software debugger for the Myriad, and there's not a software debugger for the FPGA. Now you could go in and make a custom layer for one of those devices that spits out debug info, right? But the run that particular layer, in this instance, this QQQ layer, I just want to run it on the CPU, and then I can use vTune and go in and step through that system and see what's going wrong. So that's and if you're developing a custom layer called QQQ, that's another way to use this, is to be able to do debug that new layer in the CPU area. Now, if you're doing the custom layer, you would then have to do a custom layer in OpenCL to get CPU logic debugged. You're not getting the OpenCL layer that's running on the FPGA or the Myriad debugged, but we do have support for OpenCL. Sorry, yeah, OpenCL. Sorry, OpenCX. Oh, I'm getting lost. We do have support for those. So we're doing some debug of those layers. Let's see, execution precision. So if you've got the heterogeneous plugin and you've got a model that's is running on devices that inherently support different sizes, then you can also see there might be an issue there, right? But so if the example there is right, I want to do GPU with a CPU fallback with FP16, right? On the GPU, you make yourself an FP16 IR, right? If necessary, the weights are converted back to FP32 for execution on the CPU. Although since these slides were written, the CPU now supports FP16. If you want to do something else, the converting from FP16 to FP32 is add some zeros. There's not much you can do about it. So it's not really it doesn't make it more accurate. It just adds 16 zeros, I imagine. The CPU on the FPGA, the execution on the FPGA is done by the bit stream, so it's FP11 or FP16, and the execution happens on the CPU at whatever, probably FP16. There are, within the FPGA, there are scaling and conversion pieces of hardware that can convert from different precisions in hardware that'll do the automatic scaling. So if you see our slide deck on just the FPGA, there's a bit more information there, and it's done in that crossbar section that you may have seen earlier. Let's see. Something new that came out with R2 is multi-device support. So that's automatic load balancing, and it's load balanced at the inference request level. So it's not per layer; it's per inference request. So you can use the HDDL and the GPU and then the CPU if you want. If you use the CPU and GPU, they call it very ubiquitous because everybody's got one. Or you can do multiple Myriad sticks. It's fairly easy. Depends on the sample. You got to have a sample that's been designed to take it. But you just on the command line you supply -d multi HDL GPU. It uses a there's a newer API, the core, what we call the core API, and that allows you to use it. So you can see there's the top one and the old one supported in the new and the old APIs in R2. If you're doing it on the command line, then doesn't matter if you need your application needs to be able to read the command line and set the device priorities that you wish, right? If you FPGA on the command line, but there's no FPGA selector in your code, it's not going to work. So no, you need to have a sample that will support the multi-devices that you're wanting to run the system on. See, yeah, this is some of the I would say benchmarks or recommendations on how it's working. It's recommended for the PCAA devices, and the other ones are HDDLR. Multiple myriad sticks can also be combined, and very close to 100% utilization there. And a CPU and GPU combined, we get about 97% speed up. And by that, what we mean is if you run it only on CPU and get a benchmark, and then you run it on GPU and get a benchmark, when you run them both, you get 97% of the combo. And it will change, right? Depending on the size of the model, how much you do need to leave one core to support the GPU. It's got to be able to get the data in, so you don't try. No, if you use all 4 cores, get a benchmark. When you go and try and run something on the GPU, you've only got 3 cores out of the 4. One's being used. So that's why there's a range there. And then this TDP piece is saying, yeah, if you run it too hot, you may get thermal throttling. It's fairly easy to do. If you're running everything at 100%, it will get 100% that's used and how fast the data is coming in. As I said, CPU is the critical resource. It's the one that it's in control. So it's shuttling data back and forth for the plugins. So there, yes, if you're running HDDL, right, you need 1.5 CPU cores, all right? Depends on the model, right? But they've got, if you're using 1.5 CPU cores, if you've got this sort of 25,000 frames per second example, you're only running one every 10 milliseconds, you need half of a CPU core. A GPU takes 1 core generally, and then there may be layers that fall back to the CPU as well, so automatically. So that's the way it's done. And then, as I say, if you're using the KB Lake, which is just 2 cores, they're like, no, don't recommend using the CPU at all on a KB Lake or any other device that's just got the 2 cores, because that will. So there again, this is a rule of thumb. Every accelerator needs a CPU core. So GPU, Myriad, FPGA, you've got all 3 of those going. You need at least a 3-core machine. So that's it. And then let's say I think we've got a demo of the hetero plugin in the DevCloud as well.
Yes.
So yeah. So the other tweak or other piece that we mentioned, you will see some of the applications will be using the async API, and what that allows you to do is to call an inference and let it be non-blocking. So that inference will execute in the background. So it will use the CPU in the background, open up another thread, shuttle the data off, wait for the answer to come back on the other thread effectively, while in the foreground you can run things like getting the next frame from the camera and post-processing the results from the previous frame. It's not going to help you any, right? You got to get an image, you got to run the inference, you got to do it. But if you're running a video, multiple frames, then the total inference time will shrink to, or the total frames per second will shrink to just the inference time, plus a little bit of overhead. Whereas before, if you don't use the ASIC API, that frames per second is the max of the getting the image, pre-processing, inference, post-processing, and then go back and get the next image. So that depending on the time it takes to do the inference and how fast you can get the data from the camera, right? There's obviously going to be trade-offs there and how much pre-processing and post-processing you're doing. But if you've got multiple devices and you're doing benchmark and you do async APIs, then you can make a fair bit of difference in the performance. And we had some training last week from a customer, and they were finding that the pre-processing was taking about 8 times longer than the inference. So they had to the pre-processing to be able to get the frame that they were requiring. This inferencing was running fast enough, but the application just couldn't keep up with the inference engine. So there are trade-offs. When you're doing benchmarking, it's good to make sure that you can split out the different sections and do some timing there. Let's see. This one here, video analytics. So we have an example that runs multiple models. It's one of the demos that actually runs as part of the installation from OpenVINO. We call it demo security barrier, I think. Yeah, demo security barrier. And what it does is it uses, it detects a vehicle, it detects the vehicle attributes, and it reads the license plate model. So it's a good application to show the way you can use. You don't necessarily have to find one model that can find the whole thing. You can use the best model for that particular piece. In this instance, this is doing Chinese license plate recognition. But if you swap that model out with the US license plate recognition, then the same thing could be used in the US, but the first 2 models would stay the same. So there's something there. The other piece that's good about this application is once we detect the car, and then we detect the attributes, and then we detect the area where the number plate would be. And then we take the area from that number plate, just section, and that is sent to the recognition piece to do the text. And car, right? A big picture of a car to a license plate thing, because it doesn't make much sense. So we just send the small section. And the license plate recognition model, it's got specified accuracy if the number plate is 60 pixels higher or more. So it has to be the height of the number plate is to be 60 pixels. So that likely says the width as well, because the ratios. But provided that's there, we've got that right now. That also shows some of the optimizations you can do if you're doing if you're writing applications yourself. You can have a look at some of the examples we've got. You have to be somewhat smart, right? If you detect a car and you don't detect a number plate, there's not much point in sending it to the number plate reader, right? But it's the US, for example, we don't have number plates in the front. I've only got them on the rear. So, my car coming out of this parking lot, There's no point in looking for the number plate on the front. It's just not there. So the applications have to be written with a bit of savvy as to what you're doing in there. If you similar sort of things, like if you're counting cars going through a set of street lights, it may be maximum 60 miles an hour, right? So that will give you a frame rate and all those things. If you're looking at them in a parking lot and you're counting them coming through a parking barrier and they're stopped, you're not going to need the same frame rate. Somebody comes through the parking barrier at 60 miles an hour, you got bigger problems than reading the number plate. The trade-offs on the applications have to be made at the application level, and the speed and the things, and those as they go out to different customers, different things will be different requirements. This is, I can find a regular car that's black, and then in this instance, it's like, okay, I'll put a box around there, and there's a number plate. And if you actually run the sample, I think this diagram's been drawn on there. The car on the left, oh sorry, the car on the right that's grey with no number plate, it will detect it as a car, even though it's got occlusion, but there's no number plate, so we don't send that number plate, or the non-existent number plate, to be read for that one. This one is the one that detects the number plates. In China, on the front of the number plates, so we got Beijing and Sichuan and on there. And then this is the complete demo, and the run where we load the image, we detect the car, so we detected two cars, as I said, right? Black car and grey car. One of them's got a number plate, see that? And then that goes on to the next one. And then at that point we run some of the numbers and say, okay, so the license plate read time, right, is 5 milliseconds. The vehicle attributes, right, because we detected two cars, 6 milliseconds. And the vehicle detection time is the demos are broken up into that. And you can see on the left the different inferences. Load the image, detect a vehicle, run inference 2, classify the attributes, run inference 3, detect the license plates, and then display the results. So we've got that as one of the examples in the DevCloud for you to try. Let's see. Yeah. Okay, so we're DevCloud access. Is there anybody who didn't get their DevCloud access set up? If they could raise their hands or send a message through the chat, we'll help them figure that out. So the DevCloud itself, the way it's set up, number one, HTTP, on your browser. We have a set of development servers, so those are large machines. Everybody gets a 50 gigabyte virtual machine on that server, and that's what you log into. And you develop your little program on there. We've got preloaded programs in Jupyter Notebook, and then we set up a set of job queues. So option number 3, the ones we've got were pretty much set up to run on all the devices. CPU plus FPGA, GPU, and the Movidius stick, and then also for the HDDL card. So they batch those up. Each person gets a unique device dedicated to running that inference. So it only runs one inference at a time. So you're not sharing the inference devices, you're sharing the development servers. Or you get your own access to the development server, but it's a shared machine. Whereas the inferences are run on the inference devices one at a time. So the benchmarks that you get are, your particular benchmark. You're not sharing the. This is what it looks like. So if you look on the top row, on the right, you can see some IEI tanks. The next row down has got the same, but just little black boxes in the foreground are some of the Atom devices, Apollo-like devices. Some of those, I believe, have got Movidius devices plugged into them. So we can run pieces like that. This is available for for a week. This code that you've got. No, this is not. This is.
Yeah, that's not the right code.
That's the right code. That's the code from like the last event. Yeah, so you gave the code out to people. It will be valid for 7 days. If you need longer, just let us know. We can help and get you set up with a longer code. You would have done. I think that's about it. So we're ready to go to the DevCloud now, Shane, I think.
Yes.
Okay. Do you want to run that through the first time?
You want me to run through one example?
I think that might be a good idea.
Let's see which. Okay. Let me share my browser.
And just before we do, check. Does everybody have their DevCloud access?
I don't see anyone says no.
Oh, okay. So basically, how it works is the first time you log in, it will take first time you click on Connect or Experience.
Right.
Yeah, it takes. It has to provision that 50 gigabyte server, so it will take. So do that now, and you'll see a little thing flying around. Because Shane's done it, he's going to skip right through it and get to the
right. So once you have the access to DevCloud, you should be able to get access to this page. On the page, if you scroll down, you have your name and your user ID for this DevCloud, and this is valid for a week. All right. So on the page, there's like 3 buttons you can click, also available on the top bar here. That's introduction, experience to introduction. And that's kind of basically same thing, but a shorter version of what we have already covered today. It's explanation of what's OpenVINO provide and what's the model optimizer and inference and what's the available hardwares and plugins. And you can go through that later. And then we want to click the experience. So that one will explain how it works, the same slide we just talked about. And then if you scroll down, there's 2 buttons on the bottom. And that one is the OpenVINO in Python samples. Another is we're going through the Python examples. So you can click this button and it will direct you to another page. So that's the Jupyter Hub. So it's reading the Jupyter notebooks on the server and checking what's the latest samples listed on the hub.
So that's where you might, if you're doing it for the first time, it'll take us slightly longer than Shane did there.
Yeah.
Because it has to provision that 50 gigabyte server.
Okay. Cool, thanks. So do we want to wait everybody seeing this page now? Okay.
So it's only one page, and then you click the arrow. Yeah. So it's yeah.
Yeah. Once you are in this page, just click the run the cell, and it will run it, and it will tell you when the catalog is refreshed, and you can refresh the catalog next time you log in. But I think every time it will refresh that.
I think what it is if somebody's updating the GitHub with the samples, it won't be updated right now. Yeah, so it will now tell you if somebody's changed it, and you can go out and get a newer version.
Okay. So for now, I think nobody is.
I've seen it.
Oh, and if you scroll down, you can see a list of IoT examples for the intelligent distribution of OpenVINO in Python. Let's go through this object detection one. I think that's the one. Oh, that's tutorial. Let's go through this one. Object detection. So that one will send the job queues to all the available platforms. So if we go to lab, we click that one. So this one is the car detection demo. How it works. Okay, just simply go through that. This one we're using a single shard detector and using the ASIC API of Inference engine to detect cars in a video. And then we can send the inference job to all the available platforms, such as the Intel Core CPU, HD graphic GPU, Movidius neural computer stick and stick 2, HDDR-R, that's the VPU PCIe card, and this HDDR-F, the FPGA card. So all the available accelerators to run. And you can get the result back, and it will draw a graphic to comparing the FPS and millisecond per frame. So you will have a vision of which platform runs the speed of running an inference. All right. So the first step here is set up the dependency. So just click this one. And we'll importing some Python dependencies. And next one is we want to create a of the model. So the first thing is we need to have a model. So we're going to use this model downloader to download a model. So this one, if you install OpenVINO toolkit on your Linux, this is where the model downloader located. It's also a Python-based application. So you run that with the model name and some options here.
It's the output directory, I think. Yeah.
Yeah, directory. Yeah. Go to the raw model. So that one will automatically download the model from. It's basically reading a JSON file. I think that one we get that model. So it will get this model from the link and put the output to the directory you put here. So here we put it into the raw models. Okay, so once you have this raw model, you want to run the model optimizer to convert it to the IR format. So here we know this model is a Python, it's a Caffe model. We're using mol pi and putting the input model, the path here. So that's where this Caffe model was downloaded, and we want to convert it to the FP32, the output. And those scale and the mean values are coming from the model itself. All right, let's run that. You can see input, output, and not specified batch. This is the FP32 precision. And once done, you will receive the success information here. All right. And we also want to convert it to the FP16 version, since we are going to run it on the neural computer stick. So that one is currently only support FP16 format. In order to run it, we have to convert it to. Difference is when you run the model optimizer, you put the data type to FP16. All right, so it's done. So now we have two IR format. One is FP32, one is FP16. And then we go back to the Python application itself, and we're going to create a plugin. So this is the Inference engine API. We're using the API to create a device, and the device was defined from previously. Where did that one define?
I think it's actually inline in the code.
Oh yeah. Okay, and then we read the IR of the model since we have the XML file, so we'll read that one, and then we can load this network into the plugin. We do the load, and then we pre-processing the image, like talk about. The image itself is RGB interleaved format. So for the inference engine, it only accepts the plan for those image to that format. All right, and then resizing the frame to matching the input of this model. All right, and then we run inference on a single frame. Do that. Run inference. We are loading those models, doing that. So this should be the first frame of this video. All right, and then we want to run a video. So let's first see what the video looks like. It sounds great on my computer, but that's basically the video we're going to do doing the inference. Or detecting the cars running towards us. Pause that. Okay. And then how video inferencing works. So we will need the OpenCV API to read it either from a camera or from a video file. So you need to using the OpenCV video capture API to get the video. Yeah, this is an explanation. All right. And since we are going to send create a job file and then send the job into the queue, since the multiple users are using the same platforms at the same time. Then we need to create a job file and sending the job to the queue. So this is basically a script to how to create a job queue, how to create a job and then send it to the queue. I think, sir, we have a question in the chat window. We have Arlene says got an arrow in create plugins
section. Let's go back. Create plugin section.
Okay. Create plugins here.
Okay, so check that the previous block was run.
Right. So you cannot skip the steps, previous steps.
So check that there's a number. In this instance, we've got number 4. We've run it 4 times. Actually, it's the 4th thing to be run. So check that that's done.
Right. If you run all the previous blocks, this create I want the 5th one.
Yeah. And if it the other option is just run it again. You can click the arrow one more time.
You can click kernel.
Yeah, there's nothing much. Yeah, you can clear all the inputs, or you can just rerun it. That particular one, but if it's finding the error, right, there's really not much to it. It's just going out and finding that AVX piece.
So I will continue.
I think that, hopefully that fixed it.
Right. So after we will come back to create a job file here. So after we create, we can optional change in the video quality. This is the option. You don't want to do that. But here,
yeah, you can have a look at PBS nodes. That shows all the boxes in the
around this. So this one gives you all the available platforms on the DevCloud. So we can see there's IR Tank with the Intel kernel R5, and that's the Skylake CPU with the HD 530 GPU, integrated GPU, and that one with the RAM 8 GB, 1 GB hard drive, and all the other setups. So you can see the IR Mustang V100 and MX8. That's the 8 VPU version on the PCIe card. And this one is the FPGA card. It's Mustang F100, and that's the FPGA card. And we also have the NCS2, Neural Computer Stick 2. And I think we also have an Atom CPU here. Where is it? Oh, I think they removed an upskirt board, right?
No, they got an Apollo Lake.
Here you go. Apollo Lake.
Oh, you got Apollo Lake.
Yeah,
and there's Apollo Lake 1 with NCS2s on it too as well.
Right.
There's 15 of those. So the number on the left column is the number of physical systems in the at Colfax in the lab. So if you want to run on the KB Lake, you're waiting a little bit longer because everybody else is running. We've only got one.
Because there's only one, and I think most of them, they have most AI tags, right?
Yeah, exactly.
All right. Okay, so this is a list of available platforms, and then we want to submit the to run it.
Yeah.
Set up the OS environment, and so now then next you run, if you want to run it on fully on CPU. So we submit this job, and we'll see the process of running this inference. So how much time is spent on pre-processing and inferencing and rendering the output image. You can click them all and just wait.
Yeah, if you click, as you're doing this, just click them all and run through the fact queue. So there's nothing running yet. Yeah. So
put them in the AI tank, obscure. This is Atom CPU, and we can check the progress.
yeah, so this is the place to stop. If you go further on, you'll get errors because it's trying to report results for things that have not been completed.
Right. If you're going further, and that one will have you to review the results. Since you have not received the results, then you will have error. Let's pick one, and we'll give you nothing found here. There's no result here. So we just wait at this stage until right.
You're waiting in a long queue. Oh, you got one. You got an FPGA. There you go.
Right. It's like a lot of people are running this at the same time.
Yep, well, it's good that they are.
Yeah, that's good.
We could support about people. 2 sets of 50 is what we've had before on this system. Up to will take a while. Yes, they all take a while. And some of it's just dependent on the hardware, and others it's dependent on the number of people trying to run on that hardware. But yeah, the up to is generally the slowest because it's the slowest processor. They're generally all done in about two or 3 minutes.
It is running slow. It's not because the inference taking this such a long time. It is because
Yeah.
So I'm trying to explain that. Oh, okay. I got another. I think I got another question here.
Can you imagine trying to do all of this through Demo Depot? It would take weeks.
What you mean? If you get the hardware?
To get the hardware, to set it all up, to transport it out to a customer, and then to demo it.
Yeah, correct.
It takes us about
such a time saver.
It takes us about a day. Now, generally, it's a week of getting out there, setting up the room, running the class for 2 days because it's a 2-day class.
Oh yeah, I've lugged all those flight cases that the laptops go in.
Yeah, take it apart and fly back. So yeah, it's 4.5 days depending on travel time and stuff. But yeah, so yeah, it's a definite benefit, especially the thing you can't do at any of these face-to-face classes is give everybody a tank and all these other systems. Now, Shane, I think you've got the stats.
Yeah, but we have a question in chat window. So I think Arlene still cannot pass the create plugin session, and the first 3 sessions were all successful. What does number mean next to the plugin? If says in 19 means it will run this this block, the 19th command you will run in this Jupyter notebook. But I think the previous there's
What's the can you paste the error into the chat, Arlen? I don't see the chat.
Right. I think I have the only thing my job.
Yeah, you're finished.
Complete. I think that should be the obscure one, right?
Okay.
Now I can go to the very last one and click this one. You should see the performance graphic. Yeah. So the only one has not completed is the Intel Atom. So that one is it kind of embedded CPU, right? It's much slower than the Core and Xeon.
That's the Apollo Lake.
Right.
Arlen, that's the code that's in the thing. Is there an error message that came with that? Because we've all got the same code as you, so that's not. We need the error code,
right,
for running that piece of code. I show up to yeah. Yeah, so
The NCS2 comparable to the Core i5 GPU.
Yes.
That's not bad going.
Yeah, it really depends on the model, right? Oh,
I take it that's not Iris graphics.
What's it? It's a i5.
Yeah. Let me run it through Arc and have a look.
65. It's a Skylake Core i5. Yeah. Yeah. I mean, the other thing to think about is was it 3 watts, 4 watts?
If that, yeah.
Yeah. The CPU, you're using one CPU core and a GPU. So yeah, it really is very I mean, if you look at the graph that we had up at the beginning, right? Cost, flexibility, power, the VPU dedicated devices, that's what they're built for, right? So you put in 3 watts, you get general purpose device.
It's get a better FPS per power, right? Per watt. Yeah.
Per power, and probably per dollar too. No, yeah. The especially because we're talking NCS2 is a no, the retail price is 69, right?
Yeah.
So yeah.
Okay.
Just if you bought them more than one at a time, they would be cheaper.
Well, I'm the guy to speak to for that. Yeah.
Okay, so for the users, you can skip step 3, view the results. So that one basically just gives you the replay of the video.
Gives you a video, yeah. It's like
with the rectangular on it. So
yeah.
You don't have to run all of them, but you can scroll all the way down to see the performance comparison. If some of the job has not been completed, you can also run it. But you just like me, there is one.
There's one that doesn't seem to have run.
Yes.
Is that either not run or is it just? No, that's your Jupyter Hub. That's the screen you're looking at. You can run it. It's still chunking. It's stopped. The pre-processing.
Rama said it will eventually we'll go through that, but just take a longer time. Sometimes he said the obscure board can go dead and will automatically restart it.
All right, yeah, because that's 59 seconds. It's been longer than a minute.
Yeah.
Yeah, so that happens.
Okay.
Stopped.
From here, I think the best FPS running on this, I think this mobile SSD, right? R-R VPU card can go as high as 430 FPS.
Yeah, and it's got, and if you think of it, it's got 8 times the Intel NCS2.
Mm-hmm. Yep.
So 8 times 55 is 440. All right. So within, is my math right? Yeah.
Yes, almost there. 40.
Exactly. So within the time frame of starting and stopping and getting it going, it's surprisingly 8 times faster than a single stick.
But that makes sense.
Yeah, it's amazing, isn't it? No, math. Cool. Yep. So that's, yeah, and you can, now we've done it before where you can shut down devices. It's fun, actually, if you've got one of those devices and you've got an MX8 and you plug in an extra NCS2, the software automatically detects it and says, hey, you've got a 9-way card. And it runs 9 times faster. Because the devices are the same and the interface through PCI Express shows up as a USB, the HDDL driver just counts the number of existing Movidius. 9-way card. You plug in another one, you get a 10-way card. If you plug in another card, you get 2 by 16 because you can run multiple cards as well. So you get 16.
Yeah, and we have questions in the chat window, and Binish asked, this code does not give accuracy comparison for various inference engines, but is there a code example that does that? And Priyanka answered that question. So you can try the benchmark tool to do the comparison. That will give you a more accuracy comparison.
Yeah, the accuracy. Let's see. Are you thinking the accuracy between different engines? Yeah, there's very little difference, honestly, between running the different engines. I've like on a video, it's like 1 or 2 pixels on the bounding box. And to me, it seems like a rounding error. So going from CPU to GPU and looking at the output file. But yeah, if you use the benchmark tool, the inference is there's a SqueezeNet example, and if you change out the squeeze because it literally spits out 10 objects. It does a top 10, so you get top 10 for the image that you put in. And if you run a different model, you'll get top 10 for the next model. The other place to look, I'll see if I can find it, is just the model itself. It's got each model that we've got has an accuracy statement.
Can the benchmark tool be run from within the Jupyter notebook?
I think it can from the command line.
Is that installed on DevCloud? I'm not quite sure.
I'm not sure if it's there on R1. The DevCloud is currently running R1.
I
think the benchmark tool is preview in R2.
Yeah.
So new.
Okay.
But you can get a login prompt, so you can get a terminal on the server. All right. So the benchmark tool will run on the tanks. You can't get a login to the systems with the hardware.
Right, I can show how to get to the terminal. If you go back to the home page, there's another connect, right? You click that one, and I think you can go to the Jupyter Hub.
Actually, it was there on the thing, yeah, and then new login.
And then you go to the terminal. Yeah, that's just basically like a Ubuntu desktop.
If you type DF there.
DF?
Yeah,
right?
DF, yeah. You'll find That's the server. Right. So these are all the users. That's us all logged in, right? Those temp FS things are the 50 gigabyte users that we've got.
Yeah.
So you're on the server. You fortunately or unfortunately, you don't have root access. So if you need to run anything that needs sudo, you can't. You can't do that. But you can upload images. You can upload videos. You can upload models.
Right.
You can then run those on the DevCloud devices, or this system's got. If actually go to Intel on this one and see if.
Okay.
on that prompt. Intel OpenVINO.
That one is running. Yeah.
2019 one. Yeah. So if you go into that one, you can run the SqueezeNet example, and that gives you that's the one that I was talking about. It's deployment tools demo, I think.
Yeah. And we can run the
demo SqueezeNet. Sorry.
SqueezeNet.
Let's see. It depends on. Yeah, you can't get. You don't have access. Yep.
Right. And if we run you don't know the password. Yeah.
Exactly. Not one Intel 123. I'm pretty sure. Because I tried it.
It just don't allow you to do that.
Yeah. But OpenVINO is installed on this system. So if you've got something that can run without. So the examples can run, but it's I don't know if
you can clone some like workshop content and then run the sample examples.
exactly. Yeah, I think the workshop might be there.
Yeah.
But yeah, there's a full installation of OpenVINO available in that 50 gigabit. So if you just want to run stuff and try it, you can do that. If you want to run it on the different pieces of hardware, you make the job file and send it to the systems.
And if the customers are coming from the healthcare area, there's also two samples. Is this healthcare application? It's pneumonia classification sample. You can try that. And another is the brain tumor segmentation sample. So this two is healthcare related. The rest of that, there's intruder detector, people count system, restricted zone notifier. Yeah, a bunch of them. So I have a question. Let me see, chat window. I didn't catch it, but how do I run benchmark tool?
Yeah, sorry, you can't. So you need to install it and run it on your own system. The benchmark tool.
Go to open.
Where can I install it from?
Web page. You can search Intel OpenVINO online, and you go to the downloading page. For now, it's the 2019 R2, and R3 will be released tomorrow, right?
Okay.
Yeah. So start with 20 to 30 minutes and see if people have questions, right? I think I can send out the survey link for now. All right, you guys do it there. So I am pasting a survey link in the chat. And you can select the September 30 remote one, and we really want to hear your feedback. Yeah, thank you for joining. So you have the access to DevCloud for next 6-7 days, so you have plenty of time to try out all the examples. And we'll be here for another 20 to 30 minutes. So if you have any questions, we can answer that.
Cheers, Shane.
Thank you.
And thanks, Stuart, if you're still about.
Actually, well, this is the DR workbench running on my virtual machine. So it's kind of like slow, but it just give you an overview of what it looks like. Once you have installed OpenVINO R2 or after tomorrow, we will have R3 available. You will see something similar to this. Where are you there? So actually I'm following Store's instructions to build this one. So it's a Docker-based one. Okay, Stuart's house, the power of his house just tripped off, so there's no Wi-Fi, lights, and AC for now. So anyway, this is what's the DR workbench looks like. So you can get started, and you can import a model or import from, this is like from local. You put the local path here, or you can import a model from the model online. So once you choose the model, and then you can pick a data set. Same thing, you can either using a data set available locally, or you can go download the available data set online, and then you run or generating some random data for the model, and then you run the you set up how many set up the batch size, set up how many requests you want to run for the inference, and then just wait. So it will run all the different configurations. You already set it, and answer the comparison. So looks like content. Yep. Eventually, on the workbench, so you pick, find the data set, and then set up inference type. What's the how many streams, and then batch size, how many requests, and then it will run and give you drawing a picture. Okay, yeah. Thanks. Wait a minute. So I'll be here for another 15 minutes, and then we just call it a day. Okay.
Hello?
Fill the ellipse. Yes, for the forum, let me search it for you. Let me find that.
Hey, Shane, there's a few links I can put up if you want.
Sure, go ahead. Thank you. I posted a few links available. Yep. So developer zone forum is the last one. Okay, thank you. Welcome back.
Thanks.
It's the right time to get the power off.
Yeah. Almost. So did you get the?
Sorry, the sound was choppy.
Did you get the workbench going?
I just shared the workbench on my virtual machine and just the overview. What does it look like? Since it's running pretty slow on the virtual machine, I just tested out. Will run forever. And shared a few pictures in your slides, the one you shared with us.
Okay. Yeah. Yeah. Running on. My audience seems duplicate.
It's kind of like slow. Your voice is choppy.
I have two camera, two microphones. So echo.
Okay.
I'll close it. One.
And it sounds pretty slow. Yeah. Like 0.5 times of your speed.
Oh, it sounds really slow.
Yeah.
Oh.
Start. I can finish here, right?
Yeah. Unless there's any final question.
I don't see any questions in the chat window. Peter shared a few useful links, and you shared another.
Yes, I think Binish was looking for benchmarks or accuracy.
Yeah.
So I'll send it. I know Binish.
Okay. Here, that's.
I was hoping to have a demo of NCS2 and RealSense camera.
You want demo now?
I was going to demo, but it's crashed. It was all set up. Dunk.
Okay.
But I downloaded it from Movidius app zoo. Ran out of the box.
Okay.
Yeah, that Kickstarter's for a new bundle that we've just put together for the neural compute stick, and the pricing is pretty good, at least for the first one.
Oh. My audio sound better? No.
Oh.
Weird. How about that? A little better. No, still getting an echo. Yeah, so unless anybody's got final questions, I think we'll pull the plug again. We'll reset all the clocks on my VCR. That's the atomic pi. Oh.
Trail based single board computer, and they're actually data loggers. The vendor is just across the road from Robert Noyce.
Oh, okay.
Well, from SC2 actually,
Yeah.
the other side of the campus. And the Atomic Pi itself is going head to head with Raspberry Pi at kind of the same price, you know, like $35.
Yeah, it's very. Preloaded too. Well, I think we're going to log off. Hey, is my audio sounding better?
Yes, your voice is sounding better now.
I closed down the other version of Cisco WebEx. I had two running, or two reading the microphone at least. Well, I'd like to thank Anastasia, Dimitri, the end. But Shane and I think we're going to drop off now. But if you've got any questions, feel free to hit us off our email. You can reach me on Twitter. I'm Intel_Stuart. We have another training session in 2 weeks' time, Shane, I think.
Yes, October 14th.
Yeah.
That one I will do that. Previously it's Aroy, yeah, but now it's me. Yeah.
So if you've got friends that would like to join that, let us know. We can get them signed up for that.
I can paste the link here. Let me find that. Yeah. Here we go. So if you're interested, there's another one in 2 weeks. And also, we also scheduled another one at the end of October. So that one will covering, I think Priyanka is preparing for R3 on that one.
Okay, cool.
Yeah, so that will be, so October 28th, that one should be a R3 virtual workshop.
Cool. Well, thanks, guys. I did actually learn something new.
Very good.
Thank you.
Quite a few things. Hopefully, some of it will stick.
Well, I'll say you can do it again in 2 weeks' time, and all might.
Well, 2 weeks from now, probably exactly the same content, but the October 28th might have new content. Yeah.
Yeah, we'll have the 3-part. At least the demos will be running if they're running on our. Should have the NCS stick running on the Mac and things like that. Sounds good. All right. Have a good day, and yeah.
See you later.
Keep inferencing. Or what's, I don't know, what's the word now? Is there a verb?
No.
No, I don't think so. Oh, I think I'll just open a bottle of vino then.
Okay. All right. Thank you for joining. I will close this meeting. All right.
Yeah. Bye then.
Have a good day. Yeah, bye.